both have possible and have been observed, and it has also been observed that rates are almost similar. There is no restriction, at least when hexamine cobalt is used as a reducing agent. And a lot of information has been acquired on inner sphere electron transfer reactions using organic brazing ligands. I have told that if you take thiazide or chloride, bromide, iodide, and related ligands, these are typical inorganic ligands, and they are sigma donor as well as pi donor type of ligands. Sigma donor as well as pi donor type of ligand. On the other hand, if you pass on to the organic ligand, they also influence the rate of the inner sphere electron transfer reactions, and it has been observed that the rate of such reactions are controlled by the bridge steric effect, whether the steric crowding at the bridging ligand is small or large, poor or greater. Second thing, point of attack by the reductant on the bridge, where the attack by the reductant metal center is taking place, and electronic structure of the bridge along with the reducibility. In one line, you can say that steric effects, point of attack by the reductant metal center, and electronic structure of the bridging ligand and its reducibility play plays important role in determining the rate of inner sphere electron transfer reactions. And most often, each type of ligands have been used or studies related to the uh, related to the determining rate of the bridging ligand on the substitute for this electron transfer reactions where the inner sphere electron transfer process are pathway. So these for the second order kinetics and proposed mechanism involve attack at a remote site rather than at directly bonded to the oxidant metal center. The influence of steric crowding on the rates of some reactions for pentamine cobalt 3 complex as oxidant and chromium hexacochromium 2 as the reductant has been basically examined using different bridging ligands. And some of the basic examples are shown over here. You can see that this is formate group, acetato group involving butyl carboxylate group. This H has been replaced by the phenyl group, and here CH3 the CH2OH group has been involved and has been used as a substituent of this carbon. So this carbon has got one hydrogen atom, methyl group, butyl group, phenyl group, and the a system involving one alcoholic group. And if you have a look on the rate of such reactions, you can see that for Fermat, K is equal to 7.2 per mole per second. Of course, hexacochromium 2 has been used as the reductant for all these systems. When it is H is replaced by methyl, that is substitute the steric effect has been more pronounced, has been increased. Then the steric crowding has been increased. So the rate is 0.35. And by replacing these three hydrogen atoms on this methyl carbon by CH3 groups, greater steric crowding has been basically incorporated over here, included over here, and rate has gone to much low. When it was phenyl group, as H is replaced from informate, H is replaced by a phenyl group, rate is lower. And in this particular case, one OH group has been included at the place of one of the hydrogen atoms. And you can see that rate is slightly higher. It has increased with respect to this with respect to acetate, acetato group. Here it was 0.35 and here it is 3.1. What can be concluded out of this? Simply, what has been done, steric crowding has been increase in the steric crowding, there is a decrease in the rate of the reaction. So, in one line, we can say that if the bridging ligand, steric crowding at bridging ligand increases, rate of the inertial electron transfer decreases. So, these are some representative examples which have been taken to show influence of steric crowding on rate of the inertial electron transfer reaction. Further, if another basic group is added, particularly it is in this context, including OH group, onto the carboxylate moiety, chelation of the reductant Cr2 in this case is positive. So this after deprotonation, it may coordinate through this, and due to this chelation, the rate slightly increases. And electron transfer is possible via attack on a site even more remote than the carboxyl carbonyl oxygen. So, it has been shown in the next slide. If we take this complex, simply this complex, and hexaco chromium 2 as the reductant, the rate of the reaction will be much slower. And you can imagine that in this particular case, the ligand used is simply pyridine. X group is pyridine, and it will not act as a bridging ligand, right? So, due to this, if had this it is subjected to reduction by hexacochromium 2, reaction will be much slower and will pass through the outer shell electron transfer process. And the rate has been given over here. It is 4 into 10 power minus 3 per mole per second. On the other hand, if we take isomide complex, this is a pentamine nicotinamide complex, it reacts further very quickly. The rate of the reaction is 17.4 per mole per second using the same reductant which was used with the pyridine complex. And to give it is shown over here, basically simply you can see that this isonicotinamide is acting as one of the ligands, as the bridging ligand for this particular reaction in the reduction of the isonicotinamide cobalt complex using hexacochromium, and you can see that this chromium can be attacked, can attack the carboxyl oxygen, and leads to formation of this type of moiety. So it is not the amine, it is the carboxyl oxygen that is being attacked by the reductant metal center, considering the basicity concept, and it leads to the formation of the final product. The intermediate is isoamide, which was n-bonded in the cobalt complex, gets oxygen bonded in the reductant, obviously oxidized reductant chromium metal center. And then, with the help of a table, that is, if we use simple ligands like fluoride, chloride, acetate, you can see that all these are monoanionic ligands. And you see the on the other hand, if you use isonicotinamide complexes of cobalt and chromium as a reductant metal center, the examples are the rates of such reactions are given over here. They are bridging ligand X, fluoro group, and acetato group, amide, isoamide, and simple pyridine. And these are basically oxidizing agents. This is basically reductant oxidant, and this is reductant, and this is also oxidant. If we see the reaction between cobalt 3 center using chromium 2 as the hexachromium 2 as the reductant, you can see that the rates these are basically 2.5 into 2 power 5 per mole per second. For fluoro it is this, for this acetato the rate is this. But if you see about these two ligands, amide and isoamide, what difference lies between them? Chloride, chloride, they act as a sigma donor as well as a pi donor, a sigma donor as well